Okay, so Assalamualaikum and very good afternoon. So we will continue on the lecture number 2, which on the design, okay, biomechanics and also the smart assistive system. Okay. Okay, so in this lecture there will be several topics lah. Okay, the first one is on the introduction to the autosis engineering. Okay, and then the human biomechanics for the autosis design. Okay, materials and manufacturing technologies, mechanical design and analysis of the autosis, and finally the smart and active autosis. Okay, so okay, firstly we want to talk about the definition, okay, of the autosis engineering. So orthotics is a specialized medical field that focus on the design, manufacture and also the application of the autosis. Mean that in the medical term, we as an engineer, we from the some kind of the preventive actions, we can design something, okay, to avoid some of injury, mainly maybe on the sports engineering. And then from that design we can do some of the manufacture and also the targeted application lah, okay. But in this course we are more focusing on the power tools. Mean that when we design power tools, when there are operator that use the power tools, there are possibility of the high vibration that can transfer from the tools to the humans, so that we as an engineer we can do some of the preventive action by designing the protection device, okay. So an autosis is an externally applied device, okay, that been designed to modify the structure and function of the characteristic of the neuromuscular and also skeletal system. Okay, for example, if you are using power tools, for example drill, you want to drill a hole at your home, maybe you want to mount something. So basically when the interaction between the drill and also the wall, specifically when the wall is built by the hard material concrete, so it may have transferred to your hand, okay, which you are not realize basically, but in a long term there will be some of the significant effect, what we call it the hand arm vibration, okay. So this one will be covered on the next lecture. Okay, so on the autosis engineering relies on the principle of mechanics lah, okay, the study of the force, vibration that you already learned in your previous year, okay, and what is the effect, okay. And biomechanics is the application of mechanical principles to the human body lah, mean that what kind of the design or device that can you use, and you can later apply for the human to wear it as a protection. So by blending this anatomy, okay, physiology, okay, pathophysiology, biomechanics and engineering, these devices are created to control biomechanical alignment. Mean that if people that have already get injured by some of the accident, for example, they may have some misalignment of the body, so that this one we can design device that can help them to recover from that injury, okay. So of course to protect injuries, okay, before it happen, and to accommodate the deformities, okay, and also to reduce weight bearing forces lah, okay. So this is kind of the application that we can use in autosis engineering. Okay, so this is the example of the device, okay, that we can wear, okay, for the ankle, for example, okay, and your back, okay, to support your back pain lah, okay. And also there are some kind of smart and active autosis system. Now this is the above one we call as a passive, where it has been designed specifically to support at that position, or maybe at certain value of countermeasure only. But some kind of smart device or active device can also be designed with the including of the sensors. Okay, you can include the sensors, and then the sensors you can have the brain, that controller inside the system, and then you can have the counter reaction like actuator that can always align or counteract the movement based on the situations. Okay, so this one, for example, for the ankle, and this one for the wrist. Okay. Okay, so this is the on the introduction to the automotive engineering. Okay, where we can design some kind of the smart assistive system architecture. Okay, by using the integration of the sensor, controller, and also the actuator. Okay, this may help to predictive the gait analysis. Okay, when the movement of the leg, okay, it can predict the force. Okay, and then it can soften the surface, for example, at your ankle, and then this can help you, and then also to help people to improve their walking condition and so on. So we can have some kind of adaptive resistant control. Okay, human machine interface, and so it can also be designed some kind in the research that the data can be sent, like in hospital, right? It's a cloud based data that the professor there then can make a research, okay, and then analyze the data, okay, monitoring the patient health and so on. Okay, so this is kind of example lah that been designed the smart device to help in the knee, okay, protection, and there's some kind of the value can be designed towards this orthosis device. Okay, so the modern orthosis is a convergence of the four distinct scientific discipline. Okay, the first one, okay, so basically as a history, we start to design maybe using a wood material at that time. Okay, and then when we come to this era of AI and also all the smart material, we can also improve the design, okay, and also to give a more option of material in the designing this orthosis device. So the source of this problem, basically it come from the clinical needs lah. Okay, when we have the injury, okay, we go to the hospital, and then doctor check the orthosis lah, will help to check, get what kind of injury, and then suggested the design. Okay, or maybe we as a engineer, we can look for that, collaborate with the medical side, and then we can come out with the orthosis device that in terms of mechanical, we can design it. Okay, choose the material, the right material that can help in terms of the design. And then of course we can have the study by putting some of the sensor, for example, the motion sensor. We can also study the motions, okay, that help us to predict the force that we need to use in designing our device. And finally, with this era, we can also integrate the system, okay, towards the intelligent control that can always counteract the patient lah. Okay, for example, during the walking, it can help in terms of improving by using the intelligent control, and also the data also can be sent to cloud for the monitoring. Okay, okay, so there's some kind of for integration in terms of this orthosis field. Okay, Okay, so for the human biomechanics, for the orthosis design, this is some location that has the high possibility for the injury. Okay, so targeting the structural failure points of the human musculoskeletal systems. So first one is at the neck lah. Okay, this is more towards the stability and alignment of the neck. If you get the neck injury or want to protect, okay, your neck from the injury. And then another location is on the spine. Okay, this is more towards the load distribution. Okay, if you always lift a very high or weight that in a long time it can contribute to the spine. Okay, and then for the wrist is more to trauma prevention, because sports injury. Okay, if you use okay, we use hand in more a lot of sport, right? Badminton, okay, and then there's a lot more lah, okay, that use our hand and wrist for the sport. So sometimes we need to do some of protection. We can wear glove, for examples, maybe in using the power tools device. Okay, not not specific for the sport, but for the working daily working condition also, we can have trauma prevention at the wrist location. And knee is more towards the ligament offloading. Okay, this one also when we get old in time, so our knee basically will have some effect in terms of some of the reduction in the use of the knee itself. Okay, maybe we can have some of the protection also when during the walking, okay, climbing and so on, that can protect our knee. And finally, the ankle or your foot, this is more to the gain correction and also the elderly mobility lah. Okay, same like the knee. Okay, when you get all that, this some of the function of our body and joint will be reduced. Okay, and then and there are some cases also that human that have a different gait, mean that the surface of the leg, okay, is different. Okay, so that some, if you go to the buy shoes, there are some special shop that can design your shoes based on your shape, okay, of your foot. Okay, so designing for the dynamic constraint of the human gait cycle. So this is example lah, when you walking, there are 4 condition. Okay, the heel strike. Okay, when you start put your first leg, the right leg is full on the surface, and then you start to take your leg, the second leg, the left leg, and then they are mid stance, and then the 2 off mean that you already, the second leg will be not in contact with the surface, so that the support will be fully in your right leg. Okay, and also the swing. Okay, the swing phase mean that when you want to walk, yes, kind of swing. So this is kind of the motion of the gait that basically you can measure it. Okay, and then if there are possibility to have a orthosis design to support this, so that you can design it lah. Okay, so what we can do is on the study for the load distribution, so that you can mapping the dynamic pressure points during the heel strike to prevent tissue necrosis. Okay, so you can have a sensor mounted on the surface, okay, of your leg here, so that you can do some of measurement lah. Okay, the load distribution, and then joint of kinematic and kinetics, which is to tracking the angular velocity and joint torque through the swing phase. Mean that when you are in your swing phase of your walking, so that's some of the joints may have a different speed, okay, when walking speed and so on. That's some kind of, you can do some of measurement also. And then the human motion constraint, this is to identify the absolute biological limits of joint articulation to prevent device induced injury lah. Okay, mean that you can set, okay, when you wear some device, okay, when you are walking and you feel hurt about it, there are some of the measurement that can be done to limit the value of force that also related to this load distribution lah. Okay, so this is some kind of the from the medical side, how we can translating this anatomical movement into the mechanical engineering matrix. Okay, first you can measure the force and moment analysis, okay, and calculating required counter torque to achieve the joint stability, okay, and then energy absorption. This is some kind of the thing that you can do also in mechanical engineering by designing the structure capable to dissipating impact kinetic during the locomotion lah, okay, kinetic energy during the locomotion. And finally, the vibration transmission, okay, you can modeling how resonance frequency travel through the bone and soft tissue to mitigate micro trauma. So this is some kinds of the mechanical engineering measurement that you can do, okay, and measure before you come out with your design of your orthosis device, okay. Okay, so in terms of now when come to the you have your design, and then what kind of material that basically you want to use in your orthosis device. So like what I said before, maybe during the old time we start with the woods at that time, but somehow in this recent year we have various of materials that can be used and design your device to match your application lah. Okay, so we have for example 5 of material like thermoplastic, okay, carbon fiber composite, silicone, okay, the foam, the EVA foam, and also the aluminum alloys. And this all kinds of material, we can classify it in terms of 5 characteristic, which is the stiffness, flexibility, okay, fatigue resistant, weight reduction, and patient comfort. Okay, what you can see here with the round full of the color mean that they have the maximum point lah, advantage, okay, like like the carbon fiber and aluminium alloy, thermoplastic, they have a very high stiffness, okay, but basically when the material have the high stiffness, they may contribute to less flexibility, okay, for example carbon fiber, but they can have a high fatigue resistance due to the high stiffness, okay. And the material with the high stiffness also sometimes they may contribute to the mean that the mass is high lah. For example, if you have the aluminium, okay, they can contribute to the high mass. But somehow when you have the composite, you know that composite is a less weight but high stiffness, okay, high stiffness to weight ratio, okay, is a very stiff, strong, but can reduce in terms of weight. And finally, it can also associate with the patient comfort lah. Basically, when the material is soft, it can have or contribute to the patient comfortability, okay, like the silicone, okay, the foam. But some kind of the device that have the high stiffness, okay, it may not so comfort to the human lah, because of it's hard, right? Due to the stiffness, the value of the stiffness. Okay, so there are some of manufacturing method that, okay, that you can use to produce the device based on its material lah. Okay, so I think this manufacturing method also you have learned it during manufacturing technology course in your previous year. Okay. Okay, so okay, this is some kinds of the ankle orthosis device that been designed. Okay, okay, you can use like 3D printer. Okay, and also different material. Now the 3D printer technology is very good and advanced, so that you can mix the material together to have a more targeted stiffness value and comfortability of your orthosis. Okay, so this is the cycle of we call it 360 orthosis, the step by step how you want to start to come up with your design lah. Okay, first of course you need to do a physical examinations. Okay, from that the doctor may have some of the point of data that can be provided to the engineer, the planning for the orthosis device design. Okay, and then you can have a model technique. Okay, that you can measure the force. Okay, whatever the parameters that need for the design, and then you can start producing lah. Mean that you can use the 3D printer to produce the material, and then you can test it, and finally you can see lah the results. Okay, so this is the general methodology. Okay, so this is another kind of methods that we can use in engineering. Okay, we can use 2D scan, mean that when you put your leg, okay, you can have a force sensor and do a sound mapping which of the contact that have a high force. And then you can do some of the 3D scanning also. Okay, I think in our lab at the vibration lab we do have a plate force that you can do some of the mapping, and then we also have the 3D scan that can scan your leg lah, the ankle and the foot part, so that you can come up with the data, and then you can print it using a 3D printer. Okay. Okay, of course you can do some modeling, okay, slicing, and then you can print it. Okay, and then the result is some kind of this lah. Okay, so move forward to the mechanical design analysis of the orthosis. So this is step by step lah. Okay, in terms of engineering, we can use SolidWorks to do some of the CAD modeling. Okay, of course when you get the data from the 3D scanner, it's not a complete data. Okay, there are some of the maybe gap or looping that you need to fill it. Okay, to create a more proper 3D model data lah. And then you can do the finite element analysis, okay, to simulate the stress, force, okay, during the contact using the ANSYS software. And then there are more advanced if you use Abacus. Okay, basically we have all these 4 software in our school, okay, to do a complete study of this design of the orthosis device lah. Okay, and then you can study using to see the structural and fatigue analysis, okay, using the Abacus, so you can predict the mechanical failure over the cycle, how much it can sustain of your orthosis device. Okay, and then finally you can do some of the control algorithm using the MATLAB. Okay, to do maybe some of the ergonomic refinement. I think in this MATLAB simulation they have some of the build model of the maybe the foot, okay, the waist, okay, maybe the neck model that you can use, okay, by inputting the force, and then how you can design the control to counteract the system towards the active assistive device. Okay, Okay, this is the case study how we can mitigating the high frequency trauma in the industry power tools lah. Okay, so okay, so there are some part that need to be realized or concentrate. Okay, for example, from the tool itself, okay, you may need to know the natural frequency. Okay, mean that if you need to measure so that when the operating of the tools is not coincide with the natural frequency, to avoid a very high vibration transfer to your hand lah. Okay, tuning the device resonance to avoid amplification of the power tools. Okay, so sometimes the device may have loose some of nut that can contribute to the high vibration also. And then the safety factors, okay, engineering deliberate redundancies to ensure absolute patient protection means that you need to consider the safety factor, how you hold the device and so on. So the deflections mean that the calculating the maximum level bending before the structure of logical failure mean that you can do some of measurement. Okay, so this is some kind that related basically in your assignment or report later on, where you measure the vibration from your tools and also you measure the transferred vibration to your hand. Okay, so from that you can refer to the chart and then you can do some of the decision. Is it this device have the high vibration and is it okay to use for the certain of time? And also the stress concentration. So this is some kind that you can do some of analysis also in the software kind of element to see how much the stress that been transferred to your hand, or you wear something protection, how much the stress that can be transferred to that the device. So okay, okay, so this is some kinds of to compare lah between the passive and the smart autosys device. Okay, so you can see that the passive is designed basically as it lah. Okay, they have no some kind of active counter reaction, but in the active system you can see that they have a sensor that be mounted. Okay, they will have some kind of controller. Okay, maybe a smart controller that we can put together with the assistive device, and then the controller can produce the counter reaction to the actuator to drive. I think if you watch some of the video from the, if not mistaken, in China maybe they have some kind of this support device. Okay, you can wear it and then it help you to walk. Okay, for mean that you can less use your energy with the support of the device. Okay, so they are in terms of mechanism, function and limitation that from the passive that we can improve it by integrating the active system. Okay, okay, so come to the smart and active autosys device. Okay, so basically this is the loop lah. Okay, so from the human, okay, you can wear a sensor to measure your activities. Okay, and then the signal can be sent to the controller, basically the brain lah. Okay, the controller to see how much the counter reaction force that need to support the motion, and then of course output to the machine, to the actuator itself. Okay, to do some of the counter reaction or correction, protection, and finally you can feel lah the feedback. Okay, how much that before this you need to walk using very maybe energy and more forces, and after wearing this autosys device you can have a feel of feedback that you can use less energy to walk and so on. Okay, okay, so this is more towards the control part. Okay, so you can use basically the PID control. Okay, this thing also you already learn in your third year. Okay, basic PID control, the integrating the combination of proportion